Good evening. Good evening, ladies and gentlemen. Welcome to Playground. Delighted to have you here. I have the distinct pleasure of giving you a minute or two of context onto what this building is and what we do here. Playground is a somewhat unusual deep tech venture firm. Deep tech means investing in things that almost certainly won't work, but will be consequential if they do. And we're focused on the future of computation, on semiconductors, on energy, on applications of advanced computation to tackling our most difficult diseases. And my partner Pat Gelsinger has a storied history in semiconductors that he feels like he has unfinished business in. We have companies that are building million qubit quantum computers. We have companies that are building exotic forms of matter that do computations in novel and new ways. We have companies that are changing the way lithography works to restart Moore's law against what is today our most sophisticated technologies, that of EUV lithography machines, which have become emblematic of where technology has got to, but are starved for photons and deserve a better light source to continue their roadmaps. That machine is actually emblematic of a place that I feel like some people think we've got to, which is diminishing returns, right? That these exotic ASML devices are producing less and less for more and more money, that our fabs, despite the fact we spend tens of billions of dollars on building those fabs, are returning less and less for that incremental effort. There's a feeling like we are consuming all of the world's power in order to feed the voracious appetites of white-knuckling LLMs to produce less and less interesting results. And there's a sense that maybe we are at the end of something, right? That we're grinding into this period of the end of Moore's law, diminishing returns, and these wild expenditures of capital and resources are getting less and less and less for what we put in. But I would argue that that impression may be true temporarily, but there are extraordinary degrees of freedom that we are yet to explore. We are not at the end of Moore's law. It's not dead, it's merely resting. There are ways of doing computation hitherto unimagined, right? Different architectures. We've been white-knuckling von Neumann architecture for 75 years. There are other ways of doing it. There are other things to make computation out of besides transistors and semiconductors, right? That things like superconducting logic give us the opportunity to increase productivity of computation by factor of 100, factor of 1,000. Transformers are not the end state of AI, right? AI is embarrassingly stupid compared to many of the examples we are carrying around in our heads, both in terms of what it can achieve, but also how much power it uses to do it. And that's not an end state either. There's nothing magical about nature. There's nothing magical about being able to think at 20 watts. But it's a bit embarrassing we're at megawatts, not handfuls of watts. So I think we are entering a period of incredibly dynamic change in every aspect of the way we do computation, from the light sources to the materials to the architectures to the kinds of models we run to the way we train them to the way we think about software. All of that is a jump ball right now. It's all up for this incredible rapid period of change that we all get to participate in, which is a great honor. And Playground's been lucky enough to see much of that play out within these walls. We were lucky enough to host Naveen back in the day when it was Nervana Systems, where we first invested because those guys were doing, before they had hardware, they were doing NVIDIA microcode better than NVIDIA was. And I was like, maybe there's some guys who can beat Jensen and Jensen's game. After they sold to Intel, it's like, beating Jensen's really hard, really, really hard. But it was delighted to have Naveen back with MosaicML, which demonstrated a degree of freedom right at the birth of these interesting foundation models. And we're absolutely delighted that Unconventional is back here inside Playground, because my experience of interacting with Naveen is that he is a singular focus in the world of gathering AI talent to figure out what happens next. And I think that also within these buildings, we have various forms of computation and semiconductors and logic that may inform the journey of unconventional. But it's incredibly exciting to realize that we are not at the end of anything. We are right at the beginning. And the next couple of years is going to be an extraordinary journey driven by companies like Unconventional. And we're super excited to have Naveen back. And with that, I will introduce the people who lead in the conversation. Of course, Naveen Rao, Konstantine Buhler, and Molly O'Shea. Thanks very much.
So I think this will be a very special discussion because I got to look at the guest list ahead of time and it seems like you all are super smart. So we're going to go very deep technically, and as much as you want to share, feel free to lay it out. I think it would be very interesting for the whole group to just hear all of your knowledge.
Do my best. We'll see.
He did say in the introduction that AI is embarrassingly unintelligent compared to most brains. I think I heard most brains, so it's including all in this room.
So to start things out, I'd love to maybe start at the macro perspective. We may be in the early innings of these things and the super cycle, but exactly where are we in the super cycle? What is the thick of it? What do you see going on?
I mean, it's impossible to say for sure because you have to see the whole super cycle to know where we are, I guess. But I mean, as Peter pointed out, right? I mean, even 10 years ago, we were still kind of working our way out of traditional compute workloads, that kind of a thing. It's sort of like that was the primordial mist of the next level of intelligent evolution. And I think we're at this point where, okay, we figured out some stuff. Like we can use numbers and algorithms on existing hardware to build something that's actually demonstrating intelligence and learning adaptation, but it's really bad. Like, I mean, just think about for a moment, like the errors that are made, like they're errors that are so obvious to any biological system, even like a child or a rat or something, like can reason through those. So we still have not really cracked the code on exactly how to build that. My personal take is that we need innovation on the hardware substrate to actually build true intelligence. You're not going to get there with this sort of rudimentary thing that we have. So, I mean, there's a lot of things that Peter was talking about in terms of investment. I mean, some of those things will pan out, some won't, but like, that's what we have to start doing. We have to start thinking very deep and very fundamentally. And biology always kind of broke across these different abstraction boundaries. I mean, abstractions are actually a human construct, right? We put these abstractions in place of like, okay, well, I have software and I have arithmetic, and biology doesn't work like that. Neural networks just kind of act. The physics of them act. And so how do we get to that point? It's going to take us a while to build engineered systems like that. But, I think we're, not to sound too big, but this is like building intelligent systems at the scale that we can do as a species is something that the world has never seen before. It's going to lead us into unprecedented ability to understand and build new things, which will continue to accelerate. That is the super cycle I think is interesting. It's like the next evolution of humanity.
And then Konstantin, where have the dollars been following all of that? And where are we going to go next?
There's been a lot of dollars following a lot of things. You guys probably seen the news. I'll step back and talk about the investment cycle, but where are we in the AI cycle? I'm an engineer by training, but I love history. And I often think about this revolution as akin to the Industrial Revolution. And here's the analogy that I'd use. Before the Industrial Revolution, say late 1600s, the vast majority of physical work equals force times distance, was done by some sort of biological means. 90+%, the vast majority of work. That's either humans or oxen or on occasion windmills. But the vast majority of work for humans was done by biological means. Flash forward to today, 99.999, some number of nines of work equals force times distance is done by mechanical machines. Just think about everything that made this possible. Of course, we see our biological work in the day-to-day, but think about the jumbo jets flying in and out of SFO and the amount of work that they're doing, the car that you came here in, the lights, the cameras, everything around us represent the factories that are producing all this electricity represents, I haven't done the proper estimate, but hundreds, thousands, tens of thousands, hundreds of thousands more work than humans are doing day to day. Now, that was the biological work revolution, the physical work revolution. And it turns out we didn't become disembodied. We're all still in our physical bodies. We all still go through life living in our physical bodies, and physicality still matters. We're on the precipice of a similar revolution, but for the mind. And I think that you look 20 years out, and the vast majority of cognitive work is done by machines, just like the vast majority of physical work is done by machines. So to answer your question of where are we in the cycle, I think we're actually very early on in the very macro cycle of AI. And we'll look back and say maybe 1% or 2% of cognitive labor is currently being automated globally. And at some point, we'll look back and say 99 point some nines of cognitive work is being done by machines.
And then the money.
The money follows the work. So if that's a lot of nines, we're going to be investing in a lot of companies that are solving those important problems.
To break this down a little bit deeper, could you just explain the differentiation between all the layers of the AI stack?
It's like your life, Naveen.
I guess so, yeah. All the different layers. Well, I think there's some of them are emergent layers at this point, but we built up on a foundation of computing that it took the last 50 to 80 years, depending on how you want to look at it, to evolve. So that was first, we had vacuum tubes, but we kind of moved to this digital abstraction. We could build things that could process numbers and do arithmetic very fast. So that was the first layer, and that took a little while. I think ENIAC was one of the first high-scale computing devices. That was 1945. So we didn't get to integrated circuits until the like late 60s, something like that, and that's kind of when Moore's law started, and I would say the modern computer was really built. And so that kept evolving. Software at that point was still pretty rudimentary. I mean, I think we were kind of calculation, and just automating calculation was really what software was about. And the application wasn't really born until probably right around that time, probably the late 60s, when we started to think about an application. I mean, we had OSs and stuff like that. So the stack kept on moving up into actual real applications. So I'd say the 70s were kind of where applications started. That's when we started to have spreadsheets and word processing, this sort of thing. So that was the next layer. So first you have this physical layer, then you have a computing layer, then you have some sort of a useful piece of software. That went on for a long time. Then I would say, mobile and cloud are probably the next two big ones. Maybe you consider internet. I think internet was not really a layer in the same way, but I'm sure people will argue with me about that. But if I look at that next layer that happened, putting applications together to build infrastructure in the cloud was SaaS. That gave rise to SaaS, and that kind of took us to where we are. So AI, I think, is something that consumes all of those and works on top of it. And so now that is starting to layer, right? We have the infrastructure layer. We have like GPU, neo clouds, that kind of a thing. Then we have software on top of that orchestrates these at large scale. And now we're getting into vertical application stacks and vertical intelligence stacks. What's interesting about these verticals is that it's like, go solve, legal problems, or go solve whatever kind of problems. It actually uses a bunch of the application stack beneath it. So that's good, that's great. But much of this is built on a foundation of physics that we didn't really go back and change that much. I mean, yes, we built smaller devices, faster devices, but the principles that it's built on haven't changed in a long time.
And so you founded Nervana, you founded MosaicML, you got acquired by Databricks, became chief AI officer there. What compelled you to start unconventional AI?
Yeah, I mean, it's a good question. I think you got to look at the motivations of different folks. I mean, my motivation in this space is, it's been about this obsession of why can we not build a computer that acts like biology? The single thing hit me when I was an undergrad, like 30 years ago. And that's when I learned about 20 watts of energy in your brain, and just how biology kind of does computation. It doesn't really do computation, by the way. It's sort of it's like dynamical systems, but we can get into that later. And my whole career has been about that. Actually, when I came out of undergrad, I learned how to. I was like, okay, well, I want to build computers. How do I build those? So I actually became a computer architect. I worked on UltraSpark 3 and a bunch of processors, and did a bunch of ASICs. Then went back to school to do a PhD in neuroscience. And I'm like, okay, now I know how to build a machine. I've done it several times, sort of from scratch. I'm still no closer to the answer of why computers aren't as good as brains, right? At that time, we didn't really understand what brains were doing. I think now we kind of did, but at that time, we almost thought of brains as sort of magical. Like, this is the time of Deep Blue, if anyone remembers that. That was the chess computer that IBM had. I think it was 1997. And it was pure brute force, right? It's just like, now we've hit an inflection point of processing power where I can just go and like forward project all these different moves on a chessboard and I could beat a human. Okay, that was kind of cool. It's very clear that a human doesn't do that. I played chess. In fact, that was like a big thing I did when I was a kid. And that's not how our brains work. I did not go through and enumerate every possibility and assess it. So there's something better that our brains were doing. And at that time, it was weird. Like, if you talk to people who are sort of in the artificial intelligence domain, we kind of thought about it as magic. We had no idea. We also knew it wasn't brute force. So there's some kind of heuristic algorithm that we didn't understand. And I think what's changed between now and then is that we've learned that the heuristic is actually some kind of learned estimator. I think that was a huge breakthrough over the last 15, 20 years, is that actually brains aren't magic. They just learn estimations of the world and actually don't do calculation. To me, that was actually a big jump. And so now it's like, okay, now we got a clue as to how to build a machine that is intelligent. So Nervana was actually when that inflection point happened. So 2012 was the ImageNet moment. Everyone knows about that. And so we said, neural networks are actually a new computing paradigm. I think we need to build a new architecture around this. And it was still like, we have to leverage what was possible at that time. I mean, you couldn't go and invest $1 billion into computing for alternative platforms at that point for AI, because no one even knew what AI or machine learning was. In fact, in 2014, when I started pitching the company, outside of these guys and several other crazy investors, everyone told me no. I mean, I went up and down Sand Hill for a whole week and got way more no's than yeses, because people didn't want to build hardware. I think everyone kind of just said, oh, computing is done. Like, the hardware's done. We don't need to think about that anymore. We only build software. Completely wrong, right? Completely wrong. I knew it was wrong, because neural networks were clearly a way to define a new kind of computer. And so that was the start of it. And so eventually we did it. It became a thing. Investors in 2015, I think, started to learn what ML was. I mean, you obviously knew what it was, but what would you say was that inflection point when investors started to know?
I think the vast majority of investors didn't really look into AI ML until 2022. The vast
You
majority.
think so?
Yeah,
Okay.
I think that there was a cycle in ML in 2015 to 2017, really around computer vision.
Yep.
And the breakthroughs of computer vision. But I still think that was early majority.
Yeah,
and
you're
the
right.
late majority only happened in 2022. You were very, very early.
Yeah. So, but I think, again, there's just this idea of like, no, this is a new way to define a computer. And so, we sold too early, sold to Intel too early. I didn't know what the macro was going to look like. It seemed like a lot of money. So I was able to put my kids through college, that kind of thing, So
How much was it?
Colleges are expensive, guys.
I mean, well, think about this though, right? I went back to grad school and in the middle of my career, and my kids were born right at that time. And so it was like, I burned through all my savings. So there's a human element to these things too, which maybe make a suboptimal decision. Anyway, so fast forward then, after I was done with Intel in 2020, we started to say like, okay, well, I know the computing paradigm is not done, but NVIDIA is kind of moving along. They're moving to this tensor architecture. Can we start to extract more out of this? So we shifted our focus to the software layer, and that's what Mosaic was. And actually, we knew that neural networks are just going to get bigger. That was very, very clear. And so that was, the LLM did exist, the transformer existed, but I don't think anyone in the investor community knew what a transformer was in 2020. So we kind of took that and we said, okay, this is another inflection point that's going to happen. ChatGPT came out in 2022. We were ready to go. Now, what's interesting about, and this is a long answer to your question, but the reason I'm going there is this context matters, is I want to go back and actually reinvent the machine. And what we can do here is actually start to to use the paradigm of nonlinear dynamics. Every physical thing in the world has dynamics, has time associated with it. The physics have time. And that's something that we have not utilized in computing. We've actually tried to engineer that away. We have this very strict abstraction of hardware of being a 1 or 0 with 0 time between the 1 and 0. If I had a perfect version of a computer, I would say, do this arithmetic operation in infinite precision and do it instantly. Neither of those things are physically possible. But somehow the brain used what's physically possible with all its noise, imperfections, and properties, and I was able to do computation with it. So that's what I want to come back and do, and that's what this company's about. So this is it. This is culmination of 30 years of this, and evolution of not just my thinking, but everybody's thinking coming together. And I think we have the opportunity to completely open up a new paradigm that could exist for another 80 years.
What was step one to get the company started?
Step one. I don't know. I've been talking about this for a little while with certain investors. Ones that are
I was an instigator. I was a troublemaker.
This guy was probably step 0.
Yeah, we'd been talking about it for a while, and it was such a. I'll get into how the partnership came together, perhaps. When we think about investing in a company at formation stage, which Naveen and I got to partner at the formation stage, even had conversation before, we think about 2 things. We think about a unique and compelling insight in a big market, and we think about an outlier founder. And I'll start with the insight because that's what Naveen was just talking through, and then I'll get to the founder as well. And so the insight is just such a powerful one. As soon as Naveen and I started talking about this, we've been friends for a couple of years, but we started talking about this pretty seriously. It was an instant mind meld because I was an AI engineer by training. I was doing grad school when Naveen was building Nervana. And it has always been in the forefront, the power limitations and the compute limitations of AI. And he explains so clearly why now could be a perfect moment for analog computation, which is the reality that digital computers were adopted because of their reliability and the need for precision. It makes so much sense as soon as you hear that. Whereas AI models are stochastic. You've all seen hallucinations, but that's just one of those symptoms. The reality is AI operates in a stochastic world and analog computers do. By the way, so does our brain. If I asked someone in the audience to remember the number 37, in a week, I asked about that number 37, they might remember 37, they might remember 73, they could remember 38, 36, and they could be totally off and remember 429, right? That would be a problem. But overall, people are stochastic in how they think. And the trouble with analog computers historically was that stochastic nature. But Naveen pointed out, this is the moment to dramatically reduce power, which everybody knows is if not the major constraint of AI, and have a trade-off that's much more reasonable in the AI world. So that was number one mind meld, just awesome set of conversations. I love this idea. And then the second piece is I like thinking about things with historical analogy. And as soon as he was describing digital to analog, I started to think about the internal combustion engine. I talked about Industrial Revolution a little while ago. And with the internal combustion engine, we started the first steam engine. I say we as if I was part of it. Humanity, I had the first steam
part
engine.
Part of humanity, so yeah.
Yeah, right, yeah. Thank you. It's in 1702. And 1702 is when humanity had that first steam engine. And it wasn't until 1913 that you have the Model T and that first combustion engine that's driving a normal car. And of course, there's many innovations in the engine in between there. But the reason for that was electricity was not very reliable. So the entire industry moved towards combustion. And in college, I took some chemical engineering coursework, and I learned about the Carnot limit, which is the theoretical limit for how efficient an engine could be, an internal combustion engine. And as Naveen and I were mind melding on this, I said, this just feels like an internal combustion engine, to an electric vehicle. And then he told me about the Landauer limit, which I had not known about, which is this theoretical limit to destroying or really destroying a bit in information theory. And it made just so much sense. that just like we had a flip from combustion engines to EV for some, not all of the world, we can have a flip to analog. And so that was insanely unique, insanely compelling, just immediate mind meld, the kind of thing that you look for in this job. And then the other piece is outlier founder. And Naveen is kind of definitionally outlier founder. He's humble about his exceptional accomplishments, of course, at Nervana and MosaicML. He's also humble about being an amazing race car driver, which is pretty darn cool, and another point of bonding. But that combination basically said, I gotta be part of this formation stage, and we got to work on it together from there.
Yeah, so I think that was part of it. Like, okay, just kind of need someone to sort of push you over the top. And, you know, I was at Databricks. I did leave Databricks early from my, you know, total earnout as part of the acquisition deal. But, you know, I had the conversation with Ali and team about like, hey, look, things are working. Like, things were working great actually at Databricks. I mean, I think when I left, like when I came there, we had about a $20 million business, and it was, you know, 700 or 800 million when I left, something like that. I think it's crossed well over $1 billion. So somebody can do that. Other people can do that. It's sort of a less interesting problem for me to keep just scaling that up and making it bigger. I mean, it's great. There are people who are excellent at that. Am I the right person to do that? I can do it if I need to, but other people can do that. Let's like help me go back and innovate. And Ali was on board with that. And so actually Databricks is on the cap table as well. So we came to an agreement, then we were off to the races.
Not to deviate a little bit too much, but you were one of the first chief AI officers. Like, this role did not exist before. So what was that like?
Well, I mean, oddly enough, I did something similar at Intel as well. There was no such role there. I don't even know if it was officially ever called that, but it's effectively what I was. But I mean, you know, when you have these new roles that come up, like, I don't know, chief product officer is one of those things that came up, like 10, 15 years ago. You sort of define it yourself to some degree. And I think there is some latitude in these roles. I mean, you know, I think some of it is obviously defining a strategy around AI. That's important. Defining products, defining who the important customers are. It's kind of like being a CEO of a piece of it in a sense. But then outside of that, you know, what are your responsibilities? I don't know. I mean, I think it's there's enough latitude and it's nebulous enough that you can make it work. And I think it just has to make it fit into what makes the company successful. And so, you know, Ali and I had just sort of figured that out. I would end up doing a lot of the, you know, public speaking and press and stuff like that around AI. And that was a very hot topic, or is a very hot topic for Databricks. So I think it was good to get Databricks established in that space, you know.
What's your official title at Unconventional? Is it
The CEO?
Yeah, I feel like Naveen can't take a normal title. I think it has to be created as a new one as part of that. And you're a trailblazer. Who you are.
Everything in the company, we got to think unconventionally. So we have an un-CFO.
I saw that. I was asking for a financial update, and I heard from our un-CFO. I said, wait a second. I do want these numbers to be correct, not un.
We'll make it correct. But I think that the key is that everything about this company is about breaking the old paradigm and coming up with something new. And so it's actually really hard, like for me too, not just, you know, for any human, it's very hard to break out of what you've been taught and what you know works. So like, you know, as like we talk about analog engineers all the time, like analog engineering has largely been about making circuits act linearly, predictably. What's really interesting is if something is linear and predictable, it actually is very easy to simulate. If you can simulate in a digital system, it's less interesting. It turns out like silicon has all these beautiful physics that are associated with it. We just try to like minimize. We say like, where can I make it look as linear as possible? That's the least interesting part of it. And that's the part that everyone's been trained to go after. So now we're saying, okay, open the aperture, look at the places where it's ugly, quote unquote, right? And nonlinear. That's where the interesting things happen. And incidentally, those things are extremely hard to simulate on a digital machine. When it's hard to simulate on a digital machine, it's doing something interesting. Now it's about harnessing that and making it work for us, right? And that's engineering, and that's what we have to do. But that's where the interesting parts come from. If you're just doing something that's easy to simulate in a digital computer, just use a digital computer. There's nothing new here. So anyway, that's why everything is like you have to be outside that normal way of thinking, break some of the assumptions that you've grown up with, maybe for 30 years of your career, and think differently.
So how did you get the team together, and how big is the team?
I think the team will be like maybe 24 or so by the end of this month. Yeah, that's a hard one. I mean, we got to find people who are deep experts in their field. I mean, everybody in this company is smarter than I am on each of these elements. I am not a deep expert on all these components by any means. So at the same time, you've got to have that expertise, which means you probably did go through these kind of conventional routes and then have the right attitude to think outside of it. I think I usually do sort of the attitude check about it. It's like, well, yes, you've been doing it this way, but are you open to trying other things? Are you, what do you do outside of work? Do you do things that are, that maybe are risks that require risk tolerance? So I think these are the kind of like, personality attributes you need to build a team. And our hiring bar is very high. It takes a long time. It takes a bunch of interviews for us to hire someone. So it is what it is. We're human limited at the moment, for sure. But we are building a team as quickly as we can.
You came out of stealth in December and you disclosed a very large seed round. How much have you raised to date, and how much do you think you're going to need to raise to get this company to escape velocity?
Yeah, I mean, it's a good question. So we raised 475. There's actually interest to do more, so we'll probably raise some more in a short time frame. I think to get to actual first product, it's probably $1.5 billion is my guess. And it sounds like a huge number, but I think the opportunity is enormous. So this initial money will get us through much of the exploration and sort of not productization, but like what it takes to build a product. So there's a lot of engineering required to get from the science to this is something I can productize. Then the actual productization will probably be the last $1 billion or so. And it's just because we have to build a bunch of infrastructure. We're going to do a whole stack. Like, we're not just going to sell a chip. You can't do that because we're changing the whole paradigm. So we do need a fair bit of money to do that, but that's a few years down the line.
With capitally intensive businesses, Konstantine, I'm really curious, in the current state of the AI cycle, there's huge rounds, there's smaller rounds, and there's mid-sized rounds. But I'm curious, from your perspective, do you think these very massive rounds are reasonable, unreasonable? What becomes the breaking point?
It's all about the company. So a round is meaningless without the context of the company. And when you're set up to go after a massive problem that you're uniquely positioned to go after, that societally and individually and as an investor warrants a significant investment. In the case of unconventional, it is singular, I'd say, in their ability to aggregate this type of talent. If you want to be in analog computers, if this sounds interesting, if this is an area that you want to spend your life in and you think can be transformational, first of all, this is the company for you. And secondly, Naveen is the person to be leading that for years and decades to come. And when you can aggregate that kind of talent in one space and form the best talent in the world, and you believe that a space is sufficiently important, I think most of us would agree that massive reduction of power in order to do digital cognitive processes is sufficiently important. You can build something very large and impressive.
To go even further, how do you feel about valuations?
I'd always like them lower, Molly.
Of course. You're asking an investor.
Yeah, how do you feel about it? He wants them higher.
I want them higher.
Yeah.
No, actually, I don't. I think you want them at the right in the right range, because valuations to me as an entrepreneur are expectations, right? So when you set them higher, your expectations are higher.
That's what a good founder thinks. That is truly very good, because it is the life. I mean, you're a repeat founder. You've actually seen it. I find first-time founders are 0% calibrated to that type of thinking. And a few years in, it is very difficult for them. And then repeat founders, of whom I work with several, always have a very similar logic, because they've seen what happens, even if it's not to them, to their friends. Once they've set those expectations, and even if they surpass it, it doesn't feel as good for the entire company, or if they fall short, it feels much worse. So that is a very experienced way of looking at it.
Do you feel pressure?
No, not really. Because this is, I don't know, I just feel like this is the path I was meant to be on, right? Because I feel like this is the thing that we need to do, like as a society. I mean, just kind of put it in context. I'm sure someone in this room knows how much money do we spend on electricity generation in the world. Does anyone have an idea? I don't know, actually. I know it's a really big number. I should know this number.
A lot, Naveen.
20 trillion, 10 trillion, 20 trillion, something in this order, right? $500 million is a drop in the fucking bucket. Like it's if you can solve 0.1% of that problem, you've made an enormous company. So I think that's what it comes down to here, is that like the scale of the problem is so big. No, I don't feel pressure, because are we going to hit 1000x in the first go? Maybe, maybe not. I don't know. There's some percentage chance that we will hit it, but I think we're going to hit 50x with a very high chance. If we do that and we have a path to getting to 1000 and getting to 10,000 and 100,000, now we've created something really big. So to me, it's about like, let's keep pushing this and be as unconventional as we can, get to a new paradigm, and then keep on pushing that. That's another 20 or 30 years of innovation. So all I can think about is excitement. Honestly, I don't think about pressure at all. Of course, I have investors and I have to, make sure that I take care of them. But at the same time, like, I think they're on the journey with me,
We were talking about this a little bit beforehand, but clearly capital is not a bottleneck. Power is a bottleneck. And you have a hot take on this. Do you want to share what your take was?
Yeah, I mean, everybody here, I'm sure, has heard of all the hype, right? Everything about, we're going to do all this build out in data centers. We're going to have this giant advantage. I'm not going to name company names, but you probably know who I'm talking about. None of this is physically realizable, right? That's what's really kind of annoying to me. I'm like, okay, you're talking about, $1 trillion of GPUs. Where the fuck are you going to get the power for that? I'm sorry, right? Like you're not going to be able to build these things physically. And the things that have been realized, like the XAI clusters and stuff like that, valiant efforts, no doubt about it. And it's amazing to push through and get it done. But it broke a lot of rules and is doing a lot of stuff very inefficiently. So it's not really something you can do over and over again. To me, you really start changing the world when you make something that's repeatable and you can sustain it. When I say sustain, I don't necessarily mean from any ideological standpoint. I mean, just economically, like, can you do this thing over and over again? Does it get cheaper? Can you keep scaling it? And so that's important. You have to have this. So doing something as a one-off is not super exciting to me. Doing something where I can now, go from that one-off to something that's scalable, repeatable, will continue to get cheaper, will continue to scale, and will kind of hit these Jevons paradox sort of dynamics. That's interesting to me.
What are your principles as a founder and a leader?
Well, it's interesting because I think as a founder, you change some of these things depending on the company to some degree. Of course, truth seeking, we don't want to have these ideas of, I'm just going to defend my idea because it's mine and I don't care if it's true. I mean, you have to have this, they have to have people at the beginning of a company who set the stage and are really truly about solving the problem. Actually, I've seen this impedance mismatch happen when those people go into a big company, because in big companies, the incentives are very different many times. It's not about solving the problem. It's about getting promoted or something like that. And so oftentimes when you get these very mission-driven people in those scenarios, it causes problems. So I think being mission-driven, going after the problem and caring about it, that's an important thing. I think that's job one. I think trying to find the quickest way to get information is sort of a cultural attribute you need to have. Like, try to think efficiently, even if you've raised a bunch of money. It doesn't matter, right? It has to be about, do I need to do all these experiments? What's the cheapest way to get there? That, I still think, even at any scale, will only help you. So I think that's an important attribute. I think going after the original source of information, like, we want to keep our organization as flat as possible. Efficiency drops really precipitously as you go over like 80 to 100 people. That's what I've seen over and over again. What's that number called? 150 people. It's a particular number.
Not Mapco, no.
Some people that did the Cortex.
Yeah, but there's a word for the number. It's the something number. I forget the name now. But anyway, yeah, over 150 people, basically Dunbars. That's it. Yeah. There you go.
Thank you, ChatGPT.
Had a phone and a friend there. Yeah, so Dunbar's number, right? Like when you break that, you start to see these massive inefficiencies because coordination starts to take over. So I think keeping things flat, going to the source of information is very important. And, always just I want to be humbled by the people that I hire. I want everybody to feel that way. And we will just keep getting better. After the 20th hire, I probably would never have been hired at the company. You know what I mean? That's kind of my goal. So I think having these sort of attributes in everybody's mind just makes the company better. And it's hard to keep that going. It's just, you see it over and over again, but we're in a research mode for a while. So I think we can adhere to these principles for a number of years. So I think those are kind of the high level ideas that I like to keep.
Konstantine, what are your principles? You work with many amazing founders, including Naveen. What have you learned from them?
Interesting. I'll say for investing or for company building?
Investing.
Okay, so for investing, the first principle is honesty and integrity, without question. Working with people who are honest, say things the way they are, have clear communication with me and genuine trust. That's non-negotiable, and high integrity on all these things. It has to be a true relationship. I'd always rather know bad news, honestly, than the opposite. And frankly, that's the kind of relationship that I have with my founders, and I'm really grateful for. And partly that's because when there is tough news, which, by the way, if you do something important, there's going to be a lot of tough news. Always. If there's no tough news, you're probably doing something unimportant. So when there is tough news, the response is level-headed.
Or you're lying.
Yeah, or you're lying, exactly. And when there is tough news, the way that these relationships actually grow are by responding with ability. Taking responsibility and responding with ability and saying, okay, this is what we can do. This is how we can help you. This is how we can put this on track, or just listening and solving it together. So the first two are always honesty and integrity. And then the next is I'm looking for a spike in the person, something that they're amazing at. I'm not looking for someone that checks every box. I'm looking for someone who's unbelievable in some particular area. And the other areas we can help. That's the job. I'm not here to say, okay, well, you're really great at this, but how about we teach you these things that you don't know? Instead, it's you're great at this, be the best in the world, is the saying, run incredibly fast, and we will help complement you in the areas that you don't know. And the third is make no small plans. There's a Daniel Burnham quote. He was an architect of the World's Fair. And he said, make no small plans because they have no way of making men's blood boil and probably will never be realized. So if you're going to do it, do something big.
What companies do you think are going to fail?
I would rather not answer that. And the reality is we can get into that, but I also don't focus on that. My job is to focus on the things that can be successful. Let me think on that. If there's any category of issues. I worry about companies that chase revenue in the short term, just to be very, explicit. You can always buy revenue, and this has been true in every single cycle. It's especially true in financial technology companies and insurance companies and the like, where you can buy revenue for less. But it's even true in software businesses in an AI era where you're acquiring customers and the long-term unit economics aren't attractive. And so anytime you see a business growing really, really quickly, I like to see that the founder's thinking about the long term as opposed to the short term. So categorically, businesses that chase revenue just because it's attractive to investors and it makes the employees and team feel good, I'd be very worried. And I really like businesses. I feel really excited when I meet a founder who's taken no shortcuts and done the really hard thing up front and knows the revenue can follow.
What do both of you think about all of the circular deals that are going on at the top?
Well, I mean, there are some games definitely being played. But at the same time, I think the bet is that, yeah, I know we talk about it looks bad or whatever, but the bet is that the demand will come. And I think that's actually a good bet. So I see it as like, all right, fine. It doesn't look great in the short term. And I can see why people are irked by it because there are some sort of circular dependencies on these things. But if out of the results of this, you create AIs that start to do very interesting things, which we are doing, and real demand happens, you will see societal secular shifts. We are seeing it already, right? I think software engineering is probably one of the areas is being hit first. And I don't say hit's the wrong word. I think being changed first. And we're seeing people have a willingness to pay for those solutions. And so once that demand is established, all of these games don't matter anymore, right? It's like, okay, well, yeah, you did that deal and it pumped up your valuation, but then you grew into the valuation because the demand came. So I think that's what's been irking people, is that the demand wasn't there and many of these things happened earlier. So I actually don't see it as a terrible thing. I think I saw a very similar thing happen in the early 2000s. There were all kinds of crazy shenanigans that happened. Some of the biggest businesses in the world now came out of that.
Before we open it up to Q&A, I think we're almost there. I want to talk about race car driving.
Okay. Happy to do that.
How did you get into this sport, and how does it make you a better CEO?
Well, I got into this sport because I just like cars. I mean, I'm an engineer, and cars are a thing you can engineer. They're also beautiful and they make cool sounds and all that. There's something very visceral about them. It is sort of a form of moving art in a sense, right? And experience. So learning to do race car driving stuff, I actually just was pretty good at it when I first started. And I raced, like racing go-karts years ago, like in the early 2000s. I didn't do anything for a long time because I went back to grad school, had kids and all of these things. After I sold Nervana, I didn't want anything. I stayed in the same house and all that kind of stuff, but I wanted a Ferrari. I bought a Ferrari, took it to the track, and then that just started again. The addiction, it was like that first hit. And so then I started I started racing in that series and sort of, kept on upping the dose. And actually, I'm right in the middle of a race at the moment. The Daytona 24-hour race is happening on Saturday. I was at the track all weekend because we had our practices this past weekend. I'm literally here and I go back to Daytona tomorrow. So it's something. How does it make me a better CEO? I think there's actually a lot of lessons to learn from racing. It's precise execution. So people have this in both racing and in entrepreneurship, people have this like romanticized or just incorrect notion that like, if you're racing, it's just like, just go out, you just have like, massive cojones and you just go really fast. Couldn't be farther from the truth. Being a race car driver is about precision. It's like you hit the mark perfectly every time and it's just tiny, tiny movements, right? Same thing with being an entrepreneur. Like you have to be precise. You have to be disciplined in the way you hire and the way you talk about things and the way you focus the team. It's not something where it's just like, oh, I talk about some high level bullshit and then, everything just falls into place. No, there's a disciplined execution that happens. And so those things are actually kind of similar, just the timescales are compressed. And I think for me personally, it's just like, it's a way to just break my mind out of a local minima. It's like when you're in a race car, you're in a complete zone. Like there is nothing else outside of that. I mean, I was at Le Mans in the summer last year and, I did a quadruple stint, which is quite a long time. It's like 2 hours, 45 minutes in the car straight. I can't remember the time. You're literally just in there, just boom. I'm just doing the thing over and over again. And like you come out and you have this Zen feeling. It's really, there are probably much cheaper ways to accomplish that, mind you, but I love it.
Get a 1 week meditation retreat.
Yeah.
Just silent meditation. Safer. We need you healthy.
That's no fun though. Come on.
Yeah, do you have a key man clause or anything?
No key man.
Don't
clause.
ask about
Kept
these
it out.
things. Why do we have to go there? No, but race cars are pretty safe. So, but I don't know. It's actually, I don't know. There's a competitive element to it also, like being strategic and, judging risk. Like everything you do in a racetrack is about risk reward trade-off, right? I'm going to pass this guy now. I'm in a 24-hour race. I'm in hour 1. Is it worth it? Maybe not, right? So you have to make these micro decisions all the time, which again is very similar to running a company. Like you're constantly making tiny decisions. The success or failure of that company is a culmination of all those little decisions. Same thing in a race. 24-hour race, the decision you made over a 3 millisecond period might have changed the outcome. So make good decisions. And I think these are the kind of things you actually learn. I think there's a lot of parallels. And that's probably true for many sports, but
How fast can you go?
Depends on the track. Le Mans is probably the fastest track. We hit about 200 miles an hour on that track.
Okay, that's nice.
Yeah.
Konstantine, any hobbies on your side?
I work all the time.
Okay, well, I think we'll open it up to the Q&A if anybody has any questions. We got one up in the front. Or I guess we have mics, but
We'll come back.
it's okay.
So my question to Naveen is, what do you think of combining the physical and virtual systems? So creating a thing that's would create a new kind of symbolic system based on topology of the object. I'm talking specifically about Hopfions, but Hopfions, it's a knot of light. And so it's possible to create a kind of new alphabet or more complex just a language and describe it into Hopfion based on the topology of the object. And my other question to Konstantin is, what in case of mind, like people, the evolution of mind will be getting further. Question is, what is coming after Heidegger? Heidegger is an existentialist, and so yeah, that's it.
Well, I'll attempt to take the first one. I think you're saying virtual, and so doing it in an existing numeric machine.
The knot of light is visible in the grid.
Okay.
But combining with virtual is I mean the 1, 0, but make it
So, okay, I mean, I would argue that all computers...
Thank you for giving that one to Naveen.
So all computers are that, right? So any computation or memory does result in a physical change. We cannot represent information without a physical change. In fact, that's fundamental to this Landauer principle that Konstantin was talking about earlier. So it's about what kind of change can you use to represent information. And so, you know, we're very good at building semiconductors that can use charge to represent information, and we can manufacture those at scale. That is by no means the only way to represent information. So I think what we're doing unconventional, I would say, is can we change the way we think about computing instead of becoming fixed bit width, digital numeric or arithmetic? Can we think about it as like a dynamical system that evolves with some sort of time varying physics? If I do that, now I can represent information on physical media that have their own dynamics. First one is going to be silicon because we know how to build it. Again, when someone comes up, I said when, not if, but when someone comes up with a better way of representing information, it's smaller, you know, more energy efficient, denser, whatever, we can use that. But we have to move away from that abstraction in a sense. So I'm open to any new ideas, but we have to be able to build it and manufacture it. That's the 5-year problem. So I don't see anything else that fits that bill right now.
I'll jump into your answer about the mind and what happens next in this era where we have massive artificial cognitive scale. So there's the physical and then there's the metaphysical. I'll leave the metaphysical because that's a matter of belief and religion, and I think that is, you know, its own very important set of things. But on the physical, I think that we're going to have more and more computation doing more and more cognitive work. And I don't think that replaces the most fundamental human interactions or the fundamental needs of the mind. And I'll go back to the physical world again. Theoretically, it makes sense for all of us to be moved by mechanical objects because the cost of driving mechanical scooters everywhere, everyone in this room, being on a mechanical scooter to exert zero effort so we can move faster between destinations and doing everything over Zoom. This is a packed room, but theoretically we could do this without physical exertion at all. Would say if that technology was allowed, humans would all be sitting in front of a screen from a distance and minimizing physical exertion of effort. If that would happen, that would suggest that when cognitive processes occur, automation of cognitive processes, that will also minimize human cognitive processes and offload everything to machines. So I don't think we ever do that. I don't think we ever offload everything to machines because there's this old Greek philosopher that on the physics would say the man is the measure of all things. The person is the measure of all things. And I think that we will choose to keep our minds largely as they are, just like we've chosen to keep our bodies largely as they are even after the Industrial Revolution and the automation of the vast majority of physical work.
Guthrie, up in the front. What was your question?
If the ultimate output of AI is the completion of a cognitive task, to your point, how do you actually measure the efficiency improvement across many different types of tasks?
Yeah, it's a great question. I mean, we have a convenient way of doing that now because of tokenization. So at least in the near term, the way we're measuring it is joules per token. It's pretty straightforward. It's very hard to game, right? So, with ISO quality, holding the quality constant and joules per token. Yeah, beyond that though, you could argue that, okay, well, is the token the right atom of that task? Maybe not, right? So that starts opening up some gamification. So I think when you start moving away from that thing being the unit of measure, it starts to open this up, and that will happen, absolutely. So then it'll come down to, well, okay, how quickly can you do it or how much does it cost to do it? It'll eventually come into cost. And I think at some point there will be some tasks still that humans will probably still be pretty good at, or at least in guiding the system, because it's going to have different attributes than a human brain in terms of what it's good at, what it's fast at, what it's slow at, what it's energetically intense at, what it's not energetically intense at. So I think there will be this space where we start to trade off between different tasks at some point.
So that these previous approaches like spiking or compute in memory, they've been tried, they've been successful as much as we would like compared to artificial neural networks. Can you comment on that and how that is different from what you're thinking?
Yeah, so first off, just because something is tried does not mean it's wrong. And it is absolutely the wrong reason not to do something. I've heard that so many times throughout my life. It's absolutely not the right reason to not do something. Was it flawed? I don't think fundamentally flawed. I think it was flawed from an execution standpoint. Many neuromorphic approaches actually started very early, and it was just from a pure biomimicry standpoint. Also, I think because we didn't understand learning systems like 20 years ago, it was very hard to actually put some kind of frame in what's useful out of these. Like the question that was just asked about how do you evaluate it, that wasn't even clear 20 years ago, which now it is. So I don't think neuromorphic stuff was wrong. I think it was just maybe a bit early. Now, what we're doing differently is we're not being so literal about biology. Biology is built out of very different stuff than silicon. We are choosing silicon because we can manufacture it. The nonlinear dynamics of silicon are different than biology. I'm not saying better. I don't know if it's better or worse, but they are different. So that might necessitate different ways of thinking about it. Like spiking in a neuromorphic system, you don't need to make it spiking. If there's something if it solves a problem for us, like transmission of information or something like that in a particular energy envelope, sure, we'll do it. But we're pretty open about how to build these systems. So we're trying to build the systems kind of for what their attributes are versus like trying to fit a paradigm on top of it. So I think that's a big difference. And also, we do have these almost not ground truth, but sort of a golden model in a sense. Like I can compare it to a digital version now, which I couldn't do before. I remember the neuromorphic stuff back in the 90s. Like it was like, oh, I can, do some sort of classification or something like that, which was very constrained and not super comparable to a digital system. Now I can directly compare and I can say what I'm better at. So I think just having that framing actually makes it successful. But we're going to make it work in silicon and make it manufacturable, and it doesn't need to look like biology.
And I'm really glad you asked that because it's partly what's so exciting here. The understanding is that perhaps this is a field that has been tried. But the reality is the world is full of fields that have been tried, but have not been brought to their completion. I mentioned earlier electrification of vehicles, so the EV revolution. And that happened very recently, even though the electric motor has been along here for a very, very long time. And there are so many benefits because when you come up with the internal combustion engine, you have to deal with all sorts of physics and transmissions and coolants and all these things that you don't have to deal with when you go with just the fundamental basics of the physics of an EV. Similarly, with analog computation, there's this whole space littered with just gems of information over the decades from analog computation that the theoretical limits are even better. If you take it to the extreme of where the physics can go, it's even better. And it also reminds me of neural networks, which have gone through phases. So neural networks, I'm an AI engineer. It's been the cornerstone of my career for the past 15 years. During that time, neural networks have been out of fashion and in fashion. Not nearly to the extreme as they were in the 80s and 70s when they were completely in a backwater. But let's not forget that the folks at OpenAI were unbelievably courageous because they did something that the vast majority of academia thought was not going to work. Remember, the vast majority of academia, when OpenAI was doing their research that now has changed the world, would have thought that would fail. And you can say that with confidence because otherwise academia probably would have been working on it. So it's so exciting as an investor to find areas that have just the laws of physics and science and the promise of what can happen on their side and a great team to go after it.
I think we have time for one more question.
I have a pretty loud voice. I can go for it. Thank you. Awesome. Again, congratulations. Super excited. I have a question, where do you think is the hard wall today, 2026? Is it the energy constraint that you have to fundamentally deal with upfront? Data movement, memory, materials? I know there's a lot of race with materials, foundational materials across the world, particularly with China. So what do you envision, just going into 2026? That you're going to be
with existing paradigms, you mean?
Yeah, starting with the new paradigm that you're beginning to build, but you still have to deal with some existing remnants.
Well, yeah. I mean, if you look at an existing digital system, the vast majority of energy actually goes into data movement. So that doesn't go away. To move data, like I said before, all information has to be represented physically. And when you move information, something physical has to change. Work equals force time distance. That's still true. If it's charge or if I'm moving something around, I have to physically move it. So that is still true. And we cannot get away from this. I mean, arguably some of the optics people would say we can. Maybe at some point, that'd be great. Or quantum people would say we can. There's still a lot of hard stuff to solve there. So that absolutely is going to be there. I think from a material standpoint, lithography is kind of hitting physical limits. Yeah, we've gone to EUV. Now we have 2 nanometer, 3 nanometer, 4 nanometer. They're all very similar density. They kind of have just different attributes. Some are better at this and worse at that. So we're kind of in this now trading off space. Just to kind of give you an example, again, I go back to biology because biology is sort of an example of a system that we could have observed in the past and had gone through changes. As a trained neuroscientist, I can look at what we call the cytoarchitecture, basically the cell structure of the cortex of a rat and a human. I can't tell the difference. So the human or the evolutionary biology version of Moore's law kind of ended about 150 million years ago. The circuit didn't change very much at the micro level. The macro level changed, the architecture of the brain changed, and other things, but the circuit didn't change so much. And so I think maybe we're getting to some kind of limit there with the current lithography techniques. Now, there are people building new lithography techniques, and that's what I think is interesting. It's going to necessitate what we're doing. If we don't think about how I can use new materials that have different properties in new ways, and if we just put our blinders on and say it must be digital and it must act this way, I think that's going to limit what we can do physically. So that's actually what I'm even more excited about. Beyond just what we're going to do in 5 years, it's what are we going to do in 20 years?
And I'll say, I'll add to this, which is a perfect example of the physical world and processes where we're limiting. What I see as limiting, or the limiting factor is not talent, but the matching problem for talent. To this day, the vast majority of problems are still out there. They're ahead of us. And the amount of creativity and courage necessary to solve them is still way undertapped. And I actually do think we have immense talent in this world, not in this room, but in this whole world. And finding and developing and accessing and placing that talent in the right places is so under-optimized, so radically under-optimized. There are so many brilliant minds who can solve things in their own unique ways, and for a million different reasons are not in their best and highest use. And so that is, if I could optimize one variable to maximize the success of humanity, that's the variable that I'd push on. And frankly, it's a variable I feel like I get to work on every day.
Wow. What a good place to end. What? There was one extra question. A bonus round. Okay.
One last thing.
When do the robots take over?
No, actually. So you mentioned architecture between the rat and the human. And given your neuroscience background, the one element you didn't talk about neurocomputing that strikes me, you talked about analog, stochastic, right? That's nonlinear. It's also recurrent.
Yes.
And if you look at works of Antonio and Hanno Damasio, for example, or Francisco Varela a generation earlier, that is the defining feature, right? That the insula tracks the body state, the change. How do you think about bringing that into what you're doing? And does it play any role at all at this point, or you're just doing the neurons?
No, 100% it does. So this is what I mean by nonlinear dynamics. So if you look at these recurrent systems, we can study them in crude ways, which would dunk a bunch of electrodes into a brain and watch what happens. You actually see that like there's a ringing state. So you can perturb this state and it moves through these like transitions. These transitions actually are computation, right? That is how our brain does computation. It's done through this evolving state. So you perturb it from some kind of outside stimulus and you get this kind of computation. Those states are learnable and changeable depending upon experience. So we're building systems like this. Exactly that. They are recurrent. And we can model some of this stuff, and we have modeled it. In fact, if you look at what a transformer is really doing, like a transformer neural network, if anyone knows what a KV cache is, like you get a bunch of tokens in, you do all this stuff where you perturb the system, right? You basically, you set up a new set of desired states for the system. It walks through, it puts another token out, it jams that back in, and it does it again. That's recurrence. The whole thing is actually a dynamical system that is being simulated in this horrific algorithmic way that's order n squared in a digital system. But it is a dynamical system that sort of kind of converges. In fact, it doesn't really converge because sometimes it gives bad answers. Convergence would be giving good answers. But that's exactly what it is. It is a recurrent system. So now can we think about how do we physically build something like this that does converge and uses the physics in our favor instead of having to simulate every step of the way?
Fantastic. Okay, that was a good bonus round. Well, first off, thank you so much to Playground, Peter, Hadley, and the team here. And second off, thank you so much to our wonderful guests, speakers, leaders of the frontier of AI, Naveen and Konstantine. Thank you.
Thanks for the great questions.
Thank you, Malik. Thank you, Naveen.